What if I told you there's a star out there that breathes? A cosmic giant that pulses with a rhythm so profound. It sends gravitational waves rippling through its entire body every single day. Now imagine, what if you fell into it? Today, we're taking the most terrifying journey you could ever imagine, plunging headfirst into a Gamma Doradus variable star. This isn't just any star. This is a stellar beast that's alive with pulsations, where the laws of physics become your worst nightmare, and where your atoms themselves won't survive the journey. Welcome back to the Cosmic Atlas, where we explore the universe's most extreme phenomena. I'm your guide through the cosmos, and today, we're going to die in the most scientifically accurate way possible. But before we vaporize ourselves in stellar plasma, do me a quick favor, smash that like button if you're ready for some extreme astrophysics. Subscribe to join our community of cosmic explorers, and hit that notification bell so you never miss another mind-bending journey through space. And hey, if you survive this video, share it with someone who needs to understand just how hostile the universe really is. Trust me, they'll thank you later. Now, let's begin our descent into hell to understand what's about to happen to you. We first need to understand what a Gamma Doradus star actually is. Named after the constellation Dorado, dolphin fish swimming through the southern celestial seas, these stars were only classified as a distinct group in 1999. That's recent in astronomical terms. We've known about these cosmic monsters for just over 2 decades. Gamma Doradus stars are what we call pulsating variables. But unlike their cousins, the Kepler variables or delta Scuti stars that pulsate radially, expanding and contracting like a beating heart, Gamma Doradus stars do something far more complex. They exhibit non-rattle gravity mode pulsations. Imagine a bell that doesn't just ring with one tone, but with multiple overlapping harmonics, each vibrating at different frequencies, creating a symphony of gravitational waves that course through the star's entire interior. Let's talk numbers. Because in space, numbers mean survival, or in our case, the lack thereof. A typical Gamma Doradus star has between 1.4 to 2 times the mass of our Sun. The star we're falling into today, let's use the namesake itself. Gamma Doradus has about 1.6 solar masses. That means it's 60% more massive than the star that gives us life. It's also 1.9 times larger in radius, stretching about 1.3 million kilometers in diameter. To put that in perspective, you could line up nearly 170 Earths across its face. The surface temperature hovers around 6,906 Kelvin. That's about 6,633 degrees Celsius, or 11,971 degrees Fahrenheit. For context, the surface of our Sun is about 5,778 K, so we're dealing with a star that's roughly 20% hotter than our home star, and it's radiating 7 times more energy into space. These stars are young, cosmically speaking. Gamma Doradus itself is between 500 million and 1.2 billion years old. When this star formed, Earth was already ancient. Life had been flourishing in our oceans for billions of years. But in stellar terms, this star is barely out of its infancy. Here's what makes Gamma Doradus stars truly unique. Those pulsations I mentioned. These aren't simple surface vibrations. These are gravity mode oscillations, abbreviated as GMOs, that originate deep within the star's interior, right at the boundary between the convective core and the radiative envelope. The pulsation periods range from 0.4 to 3 days. Yes, days. While other variable stars pulsate in hours or even minutes, Gamma Doradus stars take their sweet time. Most have between 1 and 5 different pulsation periods happening simultaneously, creating a complex pattern of brightness variations that can change by up to 0.1 magnitude, subtle to our eyes, but profound in its implications. These G-mode pulsations are driven by buoyancy. Hot plasma wants to rise, cool plasma wants to sink. And the star's internal stratification creates standing waves of density and temperature that propagate outward. Think of it like ocean waves, but made of superheated plasma moving at hundreds of kilometers per second. For astronomers, these pulsations are a gift. They're like seismic waves on Earth. By studying them, we can peer deep into the star's interior, measuring its rotation rate, its internal structure, and the physics happening in regions no telescope can ever directly observe. This field is called astroseismology, and it's revolutionizing our understanding of how stars work. But for you, for someone falling into this star, these pulsations mean the environment you're entering isn't just hot and dense, it's dynamic. It's changing. It's alive, and it wants to tear you apart. Let's set the stage. You're in a spacecraft not that it'll help hovering several million kilometers from Gamma Doradus. From here, the star dominates your sky like an angry god. Its surface roils with convective cells larger than planets, and you can actually see it pulsing. The brightness shifts over hours and days, dimming and brightening as gravitational waves propagate outward from the core. Your instruments are screaming warnings. The star's magnetic field extends far into space, creating a massive heliosphere, the stellar equivalent of the bubble our sun creates around the solar system. You're already bathed in stellar wind, streams of charged particles ejected from the star's corona. Traveling at hundreds of kilometers per second, at this distance, the radiation is already dangerous. X-rays, extreme ultraviolet light, and high-energy particles are bombarding your ship. Your radiation shielding is holding ... for now. But you can feel the gravitational pull. Gamma Doradus, with its 1.6 solar masses, is exerting a force on your craft. Newton's law of universal gravitation is pulling you in. And there's no escape velocity that can save you now. You begin your fall. At first, it's gentle, a few meters per second, then tens, then hundreds. Gravity follows an inverse square law. As your distance halves, the gravitational force quadruples. The acceleration compounds exponentially. Within hours, you're moving at thousands of kilometers per second. Time dilation effects, though minuscule compared to what you'd experience near a black hole, are still present. Your watch ticks infinitesimally slower than clocks back on Earth. A tiny whisper of Einstein's relativity making itself known. The star grows larger. It fills your viewport. The pulsations become more apparent. You can see vast regions of the star expanding while others contract, creating ripples across the photosphere like waves on an ocean made of nuclear fire. Your ship's hull temperature begins to rise. The thermal radiation free light carrying heat intensifies. At 10,000 kilometers out, your ship begins to glow. The paint vaporizes. Metal sublimates directly from solid to gas. At 1,000 kilometers. The external hull reaches 1,500 Kelvin. Electronic systems fail. The spacecraft becomes a tomb of molten metal and boiling plastics at 100 kilometers. Traveling at tens of thousands of kilometers per second. You punch into the star's outer atmosphere, and that's when the real horror begins. The corona is the star's outermost atmospheric layer, and it defies all intuition, while the photosphere below is only 6,900 K. The corona is superheated to temperatures between 1 and 2 million Kelvin. This is the coronal heating problem, one of astrophysics' great mysteries. How does the outer atmosphere of a star get hotter than the surface itself? The answer involves magnetic field reconnection, plasma waves, and energy transfer mechanisms that would take an entire video to explain. But the result? You're entering a region hotter than the surface of many stars. At 1 million Kelvin, atoms don't exist as we know them. This is fully ionized plasma, the fourth state of matter. Electrons have been stripped from their atomic nuclei by sheer kinetic energy. Hydrogen is just free protons and electrons. Heavier elements exist as bare nuclei surrounded by a sea of electrons moving at relativistic speeds. Your body, your spacecraft, everything is hit by X-rays with energies measured in kiloelectronvolts. These photons tear through matter like bullets through paper. DNA molecules are shredded. Chemical bonds break instantly. Any biological matter is sterilized at the atomic level within milliseconds. But you don't just get hot. You get ionized. The extreme temperatures mean that any solid matter metals, ceramics, even diamonds immediately vaporizes. But it doesn't stop there. The atoms of vaporized material are themselves ionized. Your spacecraft, your spacesuit, your body all become plasma, a soup of atomic nuclei and electrons, indistinguishable from the star itself. The process takes less than a second. If somehow, hypothetically, impossibly some structure remained, you'd next encounter the chromosphere. This is the reddish layer visible during solar eclipses, and it's cooler than the corona above it, ranging from 4,000 K at its base to about 20,000 K at its top. Here, the density increases dramatically. You're no longer in the tenuous plasma of the corona, you're entering a region where matter is thick enough to actually block light. The chromosphere is where spectral absorption lines form, where specific wavelengths of light are absorbed by partially ionized atoms. The gravitational pull is now immense. You're accelerating at over 50 meters per second squared, 5 times stronger than Earth's gravity. But this isn't uniform. Your feet, or what used to be your feet, experience stronger gravity than your head. These are tidal forces, and while they're not as extreme as those near a neutron star or black hole, they're still enough to create differential stresses measured in millions of pascals. Any remaining molecular structures are now fully atomized. Proteins, DNA, cellular structures all reduced to individual atoms and ions. And those atoms are moving fast. At 20,000 K, the average kinetic energy of a hydrogen atom corresponds to speeds of about 10 kilometers per second. Everything is chaos. Remember those G-mode pulsations. Here's where they become relevant to your experience, or rather, the experience of the atoms that used to be you, as the star pulsates. Density waves propagate through these outer layers. Regions of compression alternate with regions of rarefaction. The temperature fluctuates by thousands of degrees. The pressure varies by orders of magnitude. If you could somehow retain consciousness, which you absolutely cannot, you'd experience the star's atmosphere as a turbulent, ever-changing maelstrom. One moment you're in a region of relatively, and I stress, relatively lower density. The next, you're slammed by a compression wave that increases local pressure by a factor of 10. These pulsations carry energy from the deep interior outward. They're the reason we know about the star's core. But for you, they're just another layer of violence in an already inconceivably hostile environment. You're, rather, the plasma that was once you now reached the photosphere. This is what astronomers call the star's surface, but that's a misnomer. There's no solid surface here. The photosphere is simply the layer where the star's interior becomes opaque to visible light, where photons can finally escape into space after spending tens of thousands of years bouncing around the stellar interior. The temperature here is 6,906 K. This is where the continuous spectrum of light originates, the light that, if you were observing from a safe distance, would tell you the star's temperature through its color. Gamma Doradus appears white with a slight yellow tinge, cooler than the blue-white of massive O-type stars, but hotter than the orange glow of red dwarfs. The density here is about 0.00002 grams per cubic centimeter. That sounds incredibly tenuous. It's a far better vacuum than anything we can create in laboratories on Earth. But it's thick enough to stop light. It's thick enough to have viscosity to transfer heat, to create the convective cells that churn the star's surface. At this point, let's talk about what you've become: plasma. This is matter in its fourth state, beyond solid, liquid, and gas. In plasma, atoms or ionized electrons are separated from nuclei, and the resulting mixture of charged particles behaves very differently from ordinary matter. Plasma conducts electricity. It responds to magnetic fields. It can support waves and oscillations that regular gas cannot. In the photosphere of Gamma Doradus, the plasma is partially ionized. Some atoms retain some electrons, especially heavier elements like iron, calcium, and sodium. These partially ionized atoms create absorption lines in the star's spectrum. When photons of specific energies pass by, they're absorbed by electrons jumping to higher energy levels. This is how we know what stars are made of, by reading the barcode of missing wavelengths in their light. The hydrogen that once formed 60% of your body mass is now completely ionized. Every organic molecule that made you, your DNA, your memories encoded in neural connections, your thoughts, all of it is now indistinguishable from the hydrogen that formed 4.6 billion years ago in the stellar nebula that birthed this star. You are no longer a person. You are statistical particles in a thermodynamic system. Something interesting happens in the photosphere. Radiation pressure becomes significant. Light carries momentum, and when photons are created and scatter through matter, they push on it. In very massive stars, O and B types, radiation pressure can actually exceed gravitational pressure, driving stellar winds that shed mass into space. Gamma Doradus isn't massive enough for radiation pressure to dominate. But it's not negligible either. The photons streaming outward from the core push against the plasma, creating a slight outward force that opposes gravity. This balance between radiation pressure, gas pressure, and gravitational collapse is what keeps the star stable. A delicate equilibrium called hydrostatic equilibrium. Your atoms cyanized and dissolved into the plasma are now subject to this balance. Some will be swept upward by convective currents, reaching the corona and possibly being ejected into space as stellar wind. Others will sink deeper, drawn by gravity toward the star's interior. Either way, your journey continues inward. Beneath the photosphere lies the convection zone, a region where energy is transported not by radiation but by the physical motion of plasma. Hot plasma rises, cools, and sinks, creating enormous convection cells, some as large as Earth itself. The temperature here climbs rapidly: 10,000 K, then 50,000 K, then 100,000 K. The density increases correspondingly. You're now in a region where matter is thousands of times denser than the photosphere, though still far less dense than water. The pressure is measured in millions of atmospheres. To give you perspective, the pressure at the bottom of the Mariana Trench, the deepest point in Earth's oceans, is about 1,000 atmospheres. Here, you're experiencing pressures millions of times greater. At these temperatures and pressures, quantum effects start becoming relevant. Electron degeneracy, the fact that electrons resist being compressed into the same quantum state, begins to contribute to the pressure. But Gamma Doradus isn't dense enough for this to dominate. That's a phenomenon more relevant to white dwarfs and neutron stars. We're now approaching the region where those famous G-mode pulsations originate, the boundary between the convective core and the radiative zone in Gamma Doradus stars. The core is convective energy is transported by the motion of plasma, while the envelope above is radiative energy moves via photons bouncing from atom to atom. This transition creates a chemical composition gradient. As hydrogen fuses into helium in the core, helium accumulates, creating layers of different chemical composition. These layers have different densities. And when gravity tries to pull denser material down through less dense material, buoyancy acts as a restoring force. The result? Oscillations. Waves of compression and rarefaction that propagate through the star at hundreds to thousands of kilometers per second. These are the geomodes that astronomers observe. They modulate the star's brightness, creating the periodic variations that define Gamma Doradus stars. And right now, you're at ground zero. The plasma around youth atoms that were once US, caught in these oscillating density waves. It's compressed, heated, expanded, cooled in cycles that last hours to days. The environment is chaotic, turbulent, and utterly hostile to any form of structure. Deeper still, you enter the radiative zone. Here, convection stops. The temperature and density gradients are too shallow to sustain it. Energy transport is now dominated by radiation photons, created in the core, slowly working their way outward. But slowly is an understatement. A photon created in the core of a star undergoes a random walk. It travels a short distance before being absorbed by an atom, re-emitted in a random direction, absorbed again, and so on. The path a photon takes to reach the surface is a drunkard's walk that can span hundreds of thousands of years for a single photon to escape. The temperature continues to rise 500,000 K. Then 1 million, then several million. The pressure climbs to hundreds of millions of atmospheres. Matter here is so dense that a cubic centimeter weighs several grams, comparable to lead or gold under normal conditions on Earth. At these temperatures, all atoms are fully ionized. There are no electrons bound to nuclei. It's a plasma of baratomic nuclei mostly. Hydrogen protons and helium alpha particles swimming in a sea of electrons. The photons have enough energy to be in the gamma-ray range, and they interact with matter through Compton scattering and other high-energy processes. Finally, the nuclei that once formed your atoms approach the star's core. The temperature here exceeds 15 million Kelvin. The pressure is over 200 billion atmospheres. The density is around 150 grams per cubic centimeter, 150 times denser than water. Despite being a gas, this is where nuclear fusion occurs. The protons that once formed the hydrogen in your water, your proteins, your DNA, they now have enough kinetic energy to overcome electrostatic repulsion and fuse. The strong nuclear force takes over at distances less than a femtometer, 1015 meters, binding protons together. The process is the proton-proton chain reaction. 2 protons fuse, forming deuterium, a positron, and a neutrino. Deuterium fuses with another proton, forming helium-3 and releasing a gamma ray. 2 helium-3 nuclei fuse, forming helium-4 and releasing 2 protons. The net result, 4 hydrogen nuclei become 1 helium nucleus. And about 0.7% of the mass is converted to energy via Einstein's equation. E equals mc. That energy is what powers the star. What creates the light you see from billions of kilometers away? Your atoms have now become fuel. They will participate in these fusion reactions, contributing to the star's energy output. Over millions of years, they'll be fused into heavier elements, cycled through convection currents, eventually transported outward, and perhaps expelled into space via stellar wind. In a sense, you've returned to Stardust. Because that's all we ever were. Throughout this entire journey from corona to core, you've been subject to those G-mode pulsations that define Gamma Doradus stars. Let's take a moment to appreciate what makes these pulsations so scientifically valuable, even as they contributed to your destruction. Gravity modes are fundamentally different from pressure modes, P modes. Found in stars like our Sun, P modes are acoustic waves, sound waves where pressure acts as the restoring force. They're essentially the star ringing like a bell, with frequencies determined by the speed of sound in the stellar interior. G modes, on the other hand, are buoyancy, Reuven. They occur in stably stratified regions where dense layers lie beneath less dense layers. When a parcel of plasma is displaced vertically, gravity tries to pull it back to its equilibrium position, creating an oscillation. These G-modes probe the deep interior regions where P-modes can't reach. By measuring the frequencies, amplitudes, and phases of multiple G-mode pulsations, astronomers can reconstruct the star's internal structure, its density profile, its composition gradients, its rotation rate at different depths. For Gamma Doradus stars, we've learned that the core rotates differently from the envelope differential rotation that affects how the star evolves. We've measured the size of the convective core, which determines how long the star will remain on the main sequence. We've even detected magnetic fields in the deep interior, something impossible to observe directly. From a physics perspective, Gamma Doradus stars are natural laboratories for studying matter under extreme conditions. We can never replicate on Earth. The core of a Gamma Doradus star contains plasma at 15 million K and 200 billion atmospheres of pressure. These are conditions where quantum mechanics and thermodynamics intersect in fascinating ways. The electrons are relativistic, moving at significant fractions of light speed. The photons are energetic enough to create electron-positron pairs from vacuum fluctuations. Nuclear reactions proceed at rates determined by quantum tunneling probabilities. No laboratory on Earth can sustain these conditions. The largest fusion reactors like ITER or the National Ignition Facility can briefly create plasmas at similar temperatures, but only for microseconds and in tiny volumes. Stars do it continuously for billions of years, in volumes millions of kilometers across. By studying Gamma Doradus stars, we're studying fundamental physics in regimes we can never directly access. We're testing our theories of nuclear reactions, opacity, convection, and plasma behavior. And remarkably, those theories work. The fact that we can accurately predict stellar properties, luminosity, temperature, lifetime's a testament to how well we understand physics. Let's put this in perspective. How does falling into a Gamma Doradus star compare to other cosmic death scenarios? Falling into our Sun. Very similar, but slightly less intense. The Sun's surface is about 5,778 K versus 6,906 K for Gamma Doradus. The Sun's core is also about 15 million K, and the fusion processes are identical. The main difference: the Sun doesn't pulsate with G-modes. Your death would be equally total, but slightly less. Rhythmic dot falling into a red dwarf, slower and cooler, but ultimately just as fatal. Red dwarfs have surface temperatures around 3,000 to 4,000 K, so you'd last slightly longer in the approach. But their cores still reach millions of degrees. And the end result is the same: complete atomic disintegration, falling into a blue supergiant. Now we're talking extreme. Stars like Rigel have surface temperatures of 11,000 K and cores exceeding 30 million K. Radiation pressure is so intense that stellar wind would start vaporizing you at distances of millions of kilometers. Your death would be faster and more energetic. Falling into a neutron star. This is where things become truly alien. Neutron stars have surface gravity 200 billion times stronger than Earth's. Tidal forces would rip you apart long before you reached the surface. This is spaghettification. When you hit the surface at a significant fraction of light speed, the kinetic energy release would be equivalent to a nuclear weapon. Your atoms would be crushed into neutronium matter, where protons and electrons have merged into neutrons. Packed at nuclear densities, falling into a black hole, the ultimate cosmic death. For a stellar mass black hole 5 to 50 solar masses, tidal forces would spaghettify you tens of thousands of kilometers before you reached the event horizon. Your last moments would be experiencing time dilation so extreme that you'd see the entire future history of the universe flash before your eyes as you cross the event horizon. For a supermassive black hole, millions to billions of solar masses. Tidal forces are weaker, and you'd cross the event horizon intact, only to be destroyed by singularity effects we don't yet fully understand. The Gamma Doradus verdict on the cosmic horror scale. Falling into a Gamma Doradus star is moderately terrible. You're destroyed utterly, but not as exotic as neutron stars or black holes. It's the kind of death that's scientifically fascinating but personally terrifying, which, let's be honest, describes most astrophysics. So why do astronomers care about Gamma Doradus stars? Beyond the morbid curiosity of how they'd kill us, what's the scientific value? Testing stellar evolution models. Gamma Doradus stars are at a fascinating stage of evolution. They're past the zero-age main sequence SAMs, the point where stars first start fusing hydrogen, but they haven't yet evolved into subgiants. By studying their properties, we test our models of how stars evolve over time. Any discrepancies between observations and predictions tell us where our physics is incomplete. Understanding stellar rotation. One of the biggest mysteries in stellar astrophysics is angular momentum transport. Stars rotate, but they don't rotate as solid bodies. Different layers rotate at different speeds. G-mode pulsations in Gamma Doradus stars let us measure rotation rates deep in the interior, revealing how angular momentum is transferred by processes like magnetic fields, gravity waves, and turbulent mixing, probing, convection, and mixing. The boundary between the convective core and radiative envelope is where interesting physics happens. Overshooting, where convective plumes penetrate into the radiative zone, affects how much hydrogen is available for fusion, changing the star's lifetime. Rotational mixing stirs material between layers, altering chemical abundances. G-modes are sensitive to these processes, giving us empirical constraints, preparing for future discoveries. The techniques we develop studying Gamma Doradus stars, asteroseismology, time series photometry, spectroscopic mode identification are applicable to other types of stars. We're building a toolkit that will let us study exoplanet host stars more accurately, improving our characterization of potentially habitable worlds. The Kepler Space Telescope revolutionized our study of Gamma Doradus stars. Launched in 2009, Kepler monitored thousands of stars with incredible precision, detecting brightness variations of parts per million. This revealed G-mode pulsations in hundreds of Gamma Doradus stars, allowing detailed astroseismic analysis. TESS transiting exoplanet survey satellite, launched in 2018, is continuing this work, surveying the entire sky and finding new Gamma Doradus stars in star-forming regions and open clusters. Future missions, like PLATO planetary transits and oscillations of stars, scheduled for launch in 2026, will push this even further. Studying astroseismology for millions of stars and revolutionizing our understanding of stellar interiors. So, we've completed our journey. From the initial approach millions of kilometers away, through the million-degree corona, past the photosphere where light escapes, down through convective and radiative zones, and finally into the core where fusion occurs. We've traced the complete destruction of matter falling into a Gamma Doradus variable star. The timeline: from entering the corona to reaching the core, probably less than an hour, given the acceleration due to gravity. Complete vaporization and ionization, less than a second after entering the corona. Fusion into heavier elements, millions of years as your atoms are cycled through the core. It's a humbling thought. The universe contains objects so hostile that our continued existence is a fragile miracle of being in the right place, stable. Rocky planet orbiting a calm star at the right time. But here's the beautiful irony. We came from stars. Every atom in your body heavier than hydrogen was forged in the core of a star like Gamma Doradus, or in the supernova explosion of an even more massive star. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created in stellar furnaces. Carl Sagan famously said, We are made of star stuff. And he was absolutely right. Falling into a Gamma Doradus star is, in a sense, returning home. It's rejoining the cycle of stellar nucleosynthesis that created us in the first place. The difference is, this time, it happens much faster and is considerably less pleasant. Gamma Doradus stars remind us that the universe is vast, violent, and utterly indifferent to human survival. But they also remind us that science gives us the power to understand even the most extreme phenomena. We can't survive a star's interior, but we can study it, measure it, and comprehend the physics at work. That's the triumph of human curiosity, even in our cosmic insignificance. We've built tools and theories that let us grasp the nature of reality across 30 orders of magnitude, from quantum fluctuations to the large-scale structure of the universe, and that's worth celebrating if you made it this far. Congratulations, you've survived a journey through one of the universe's most extreme environments, at least mentally. Now it's time to take action. Smash that like button if you enjoyed this deep dive into stellar physics. Your likes tell YouTube to share this video with more curious minds like yours. Subscribe to the Cosmic Atlas if you want more content exploring the universe's most fascinating and terrifying phenomena. We've got videos on black holes, neutron stars, gamma-ray bursts, and so much more cosmic horror waiting for you. Hit the notification bell so you never miss an upload. Trust me, you don't want to miss what we're planning next. Drop a comment below. What cosmic scenario do you want us to explore next? Falling into a black hole, getting hit by a gamma-ray burst, watching a supernova from close range. Let me know, and I'll make it happen. And if you really want to support this channel, consider joining our Patreon community. Your support helps us create more in-depth, scientifically accurate content like this. Links in the description. Share this video with anyone who's ever wondered what would happen if they fell into a star. They'll either thank you or question your sanity. Either way, you win. Finally, remember, the universe is vast, beautiful, and trying to kill you in increasingly creative ways. But armed with knowledge and curiosity, we can explore it all from the safety of our pale blue dot. I'm your guide through the cosmos. This has been the Cosmic Atlas, and I'll see you in the next video. Stay curious, stay safe, and stay far away from Gamma Doradus.